Okay, as I told you in the previous lecture, we have finished the material for the exam. I was asked to give the chapters by you, right? Could you read it out? I'll write it on the blackboard.
Some of them are the
28, 29, I'd say.
then you said only part of the chapter.
Well, in general, what determines the material of the exam is what was given in class. Most of the chapters I've covered, most of the materials that appears there. There are chapters where much less is covered, and as I said, what determines the material for the exam is what we did in class. Now, I recommend going over the lectures themselves and reading the book. It's much more important to go over the material in the lectures and the books than solving homework, previous exams. Although towards the end, once you understand the material, it's also good to do a few exercises on the material. Now, it's open material. You can bring your notes, you can bring the book, so there's no point in memorizing it. On the other hand, don't assume for the exam that you'll have time to start reading the whole material during the exam. That won't happen. It helps you if you forgot a point or you want to clarify a point. It doesn't help you if it's the first time that you see the material in the exam. That won't be useful at all. Okay, questions? Okay.
3 hours, 3.5?
3 hours. 3 hours, it's usually 2 or 3 questions with a few sub-questions in each one of them. I'll write down how many points for each sub-question. Any other questions? Okay, what I'll try to do in the next lecture on Monday is do a very short run through on everything that we did. Of course, I'm not covering all of it. I'm just giving points and trying to emphasize what from the material is important to pay attention, what were the main points in each part. As I said, I'm not going over everything. The fact that I don't mention something is no assurance that it doesn't appear in the exam. I haven't written the exam. I don't know. Okay, what are we going to do today? What I'm going to do today is address a question that was in the periphery, was somehow lingering around without us really dealing with it. And what I like about this question is that it's a very fundamental question. People sometimes get the impression that condensed matter deals with very specific, detailed properties of some material or other. And I think it's completely wrong. We are dealing most of the time with general concepts and trying to clarify, understand what stands behind it. And I'll use this this lecture as an opportunity to introduce such a concept, try to understand what are the problems that are standing behind it. I'll give also an exercise for people who are in class, which can do a small homework assignment and submit it, except for the two that have already done such a thing for and get 5% bonus. And okay, let's start. We have discussed a lot and used a lot the concept of conductance. Right? How do we calculate conductance from first principle? Okay, so first of all, we have to clarify what is conductance. So that is something that we said something about. We have a system. It's the current in the system related to an electric field applied on the system. Okay. Let's say I have my system, a lattice, and I want to calculate this quantity, conductance. How do I do it? And let me add another restriction. I want to deal here with a quantum system. Well, we got the whole business of band structure, difference between a metal and an insulator just out of a band structure. So if I throw out the quantum nature, I miss a huge part of the answer. Okay, so I have my lattice. I can describe it as a nearly free electron, perhaps as a tight binding structure, maybe even as just a particle in the box, things that we treated it in the more naive description. How would I calculate conductance out of such a system? Okay, someone tells you calculate a property of some quantum system. What is like the algorithms that you should already, as finishing your undergraduate studies in physics, start to apply?
Eigenvalues of the Hamiltonian.
Right. I'm writing down a Hamiltonian. Calculating psi I and EI, and from there I'm supposed to get any physical quantity, right? Well, I'm in a big problem here. Someone can tell me why?
What is the Hamiltonian? Does it vary?
No, the Hamiltonian would be the Hamiltonian, even so, you know what? Simplest case, a particle in a box. Okay? I'll just.
How can you define current
Yeah, the current density.
Current, you have a definition of current. You have this box calculates the wave functions. You even know what they are. 1 over V and sinus kx. X where k is between times sinus ky y times.
Don't need the 2. No, I don't need the 2 in the k definition. It's pi n over the sign.
Yes, pi. Okay. I gave you the wave functions. You know also the eigenvalues. How do you calculate out of it the current? Okay, you want to use the current density.
So this
The current operator, whoever. No one owes it. Which is a good suggestion, but it doesn't work here. Why doesn't it work here?
The current is 0.
The current is 0, and it makes complete sense. It's logical.
Returns. It's bounded, so
It's bounded. No current goes through the thing. If you ever played with a battery and a light, if you didn't connect this thing to an external lead, no current will go through it. You can stir it till tomorrow. Nothing will go through it.
you just need to, that's the new battery condition. Rather than a potential well, make it as the ends equal each other.
Okay, that's one solution which has its problems. It's a solution and it's used. But what I want to say here is that simple, naive application of quantum mechanics doesn't solve the problem of calculating conductance. We have to come and stop a minute and treat it in a different way. So, one way is to reformulate this problem as a scattering problem. You've seen some of it in one-dimensional system where you have ikx coming in and asking how much of it is coming out and how much of it is going through. I'll suggest, well, I had, once upon a time I gave a course, a graduate course, which was called 50 Ways to Calculate Conductance. Someone sees to what I'm referring to?
Course here.
Course here, but not, it's not about the course, it's the use of the phrase.
50 ways to leave your lover.
Exactly. Paul Simon. So there's people worked with all kinds of methods to so that's one problem. In order to pass current through a system, you have to connect it to the outside. Once you are connecting it to the outside, you have to say something about the outside. Let's say the same way that you're treating a scattering problem, you have a electron coming in with a definite k, and I'm asking what is the probability of it coming out, what is the probability of it reflected. Actually, this is the way that's known as the Landauer-Buttiker formulation of the conductance problem. Actually, Landauer was a very deep thinker that You should know his name, and I'm almost sure no one ever heard here about Landauer. He's the first that proved that any computation has to include dissipation, which is a very strong statement. You can't do a calculation in the meaning of a Turing machine, something like that, without to lose energy.
Oh yes, KBT ln 2, natural log of 2.
Right. So that's his invention, and this formulation of conductance is also his. He was at IBM, so the two types of problems, carrying current through a conductor and doing computation, were very much relevant to things that IBM were worried about. Anyway, I won't go into this formulation here. I want to go to another formulation which has very interesting history in physics. And how can I solve this problem of letting a current flow here without connecting to the outside?
Repeat the question.
How do I cause current to flow in this system
Thermal.
without connecting it to outside? Thermal fluctuations on average will give you a current of 0. That won't help.
The thermal difference, the gradients.
No, so I'm connected to the outside, and it won't help unless I let the electrons moving out, because like in the Hall effect, you'll get a positive and negative difference here if you try to move it, and then you'll be at a steady state with no current.
But impurities?
What will they help? I still can't pull current out of the system. I want something to flow. One solution is put an AC. You move it, AC field, and you move it in this direction and that direction, and see as at a given time in what direction is the current flowing. You won't have an accumulation of electrons just because at the end you'll move it back. At the limit of omega going to 0, you are somehow trying to connect it with the DC current. That's another way to calculate conductance, but I'm not talking about that. I'm honest to God physical realization. I'm still connected to outside. I want that I'll have only my system.
Conservation of charge. How can charge go? Where do you want the current go?
That's what I'm asking you.
Emission, radiation.
You'll see that I'm using it, but it's not not connected to the system itself. I want a system where current can flow. Okay, I'll ask you the following question. Let's say I'm doing athletic competition. Some 100,000 meter run. And one way to do it is to get the runners at the beginning of the stadium, they're running and getting out of it.
Maybe you can apply a magnetic field and then you have this.
That's connecting with the outside. You're putting a magnetic field from the outside.
And here if you didn't hear about it, I'll knock your socks off. Okay, so what do I have to use here? A torus, a ring, something like that. Okay, here in principle, you can have a current that will go around and around and around and around. I have no problems. Everything happens within one system, and I have current.
But you're putting an electric field from the outside, always.
Wait a minute.
Turn it off. Yeah, there's a current.
No, okay. Now you can say, well, what are you talking about? We know about it. How will I get a current through a thing like that?
Induction.
Induction. You are aware that if I put here magnetic flux that depends on time, that somewhere in the 11th or 12th grade you had all kinds of questions like that. In Hebrew it's כוח אלקטרומניע. In English, electromotive force. Okay. I'll do two things here. Put in the flux that doesn't change in time. And to create it, I'll put it within a solenoid. A very long, let's say, infinite solenoid, which has a magnetic flux. But if you remember anything from your high school physics, what is the magnetic field out of it? Zero. Okay, so I have no external field working on my electrons within. So what's the knee-jerk answer? What will be the influence of the magnetic flux within the solenoid? Zero. 1957. A guy by name of Bohm. Go back a few years, 1953, 1954. McCarthy times in the US, Bohm is a card-carrying communist, is teaching in Princeton, and is kicked out. Okay, he moves and does a couple of years in Brazil, and then since he's a Jew, he appears in Israel, in the Technion, takes a PhD student by name of Aharonov. And they start thinking about this problem. And here is the birth of the Aharonov-Bohm effect. Yakir Aharonov is still with us. He's 90 plus and still giving talks in conferences. Okay, Bohm had enough of this provincial
He got his PhD under Oppenheimer. Baum got his PhD under Oppenheimer.
Right, and I think he's even appears within the movie. I'm not 100% sure. Of course, he got his flirtation with communism started in this milieu of people around Oppenheimer, which is not very exactly depicted, but still has some truth in the depiction in the movie. Okay, so they were thinking about this problem, and let's follow the way they thought about it. To make life simple, well, actually they were not thinking about this problem, they were thinking on the classical problem of whether a solenoid in a two-slit experiment over almost any fundamental question in quantum mechanics goes through the two-slit experiment. And the question was, if I put a flux here, will the interference here change? Okay, but let's formulate it for this ring problem, and to make life easier, let's assume that the ring is one-dimensional. So, let's call the coordinate on the ring x. Let's write down the Hamiltonian. X just is in a moment I'll connect it to theta because it's easier and it's a bit, the notation is less cumbersome. Okay. Let's do the change of variables. So we have here why is the solution solves the periodic boundary condition. Okay. This is a problem that you should have been able to tackle within your, after a month of studying quantum mechanics. Okay, but what are we missing?
Magnetic field.
The magnetic field.
More potential.
Okay, what do we remember about the magnetic field? In general, if I have a Hamiltonian, it's already in classical physics.
Need to change the momentum.
I have to change the momentum and write instead of p squared, P minus EC times A squared over 2M. Okay.
You assume it's
What?
It's general Q, not specifically.
Well, we're dealing here with an electron. We're interested in an electron in a metal. So we put it in a ring, we're still thinking about it. If you want to define E as not the charge of an electron, you have the charge of some other particle. It's not so out of order, because people who are doing superconductivity love this problem where the charge carrying entity here is the Cooper pair, 2e. But that's not what we are doing, but you could replace E with 2q. Why is it so interesting to them? Anyone who's doing here superconductivity?
That's what creates the boson and not thermal.
Yeah, but this particular problem with the magnetic flux.
This of the flux quanta,
Hmm?
this thing with the flux quanta and
There are two types of superconductors. One, type 1, that doesn't let any magnetic field into it. One that allows a magnetic field, but in certain regions. It's called a vertex. It depends on the material. Depends on, and around it is a superconducting current going around it, which topologically is the same structures in this problem. So, okay, so what is A in this case?
It's the function that satisfies what of that the
ET.
Hmm?
Is A just E times T?
E,
Electric field.
no, I have no
It
electric
could be a
field.
gradient, right?
because the gauge.
We have no
What do we know?
that we have no magnetic
infinity
field, so it's a
it's
gradient
zero.
of a function.
Okay, we know that we're going back to not basic, but basic basic university physics. It's not even electromagnetism, it's just magnetism. right? If I'm looking on an integral over a path around a flux, should sum up to the flux.
It's true only in magnetostatics.
I said that we're doing magnetostatics, right? I told it. I'm not looking on the electromotive force, I'm looking on the simple case that the flux is constant. Therefore, I said simple and the beginning of university magnetics. Okay. In this case, for symmetry consideration, A everywhere has to be the same. And in the direction perpendicular, not perpendicular, in the azimuthal, it's called tangential to the circle, to the rings that we have here. Okay. This will give me the flux in this direction. Just check with the correct coordinates. So life is very easy. Go here. Rewrite. Well, just keep the result here. Yeah, but that's exactly the same direction.
So it's, but the left hand is a vector, and so it's A theta equal to Z.
In the direction of X, right? Life is simple here. That's why we're doing this example. So this is Px minus
Wouldn't it be convenient to put everything in terms of x or theta to do the derivatives?
Okay, in a moment I'll... Okay, phi doesn't depend on x or theta, so it doesn't really matter at this point. And px, I'll just write it down. Another simplification.
Richard, why it's only
Hmm?
why it's only the
one-dimensional. How many those do you want?
Okay, it's... Oh, okay.
We had the luck that the component of A is in the same direction as X. At this point, I can't forget about vectors because I'm one-dimensional. Life is simple.
זה כאילו הפרמטריזציה קשת, נכון?
Didn't even do any it's just a point on this ring, which I can parameterize either with x or with theta, whatever is convenient for me.
Yeah, but x as the units of length, it will be...
And if I take theta, it has the units of no units, but I have to put in this vector of r here. Okay.
You forget the square.
Correct. Okay, let me further simplify it by defining the flux quanta. A nice combination of three constants of nature. And hopefully I didn't confuse H and H bar here somewhere. Okay, and how do I solve this guy? Well, we have already the solution. The only thing that changes instead of writing two pi r, I'm just writing the circumference. So the wave function didn't change, but the energies did change. Okay. It seems, okay, we put in the flux, nothing much happened, right? No, something very important happened here. Let's write down the energy as function of n for the case, for actually both cases, with phi and without phi. So it's a parabola, and for the case that phi is equal to 0, okay. What is the velocity? Why do I want velocity? For current. I will multiply it by the charge and I'll get the current.
Shouldn't it be each bar squares?
I said that I'm...
Oh, you was
no, I think no, because
the 2 pi, yeah.
I need this 2 pi. And this guy, when appears without, is not h bar, only h. That I remember, it's a flux quantum, which again appears a lot in superconductivity. So, what is the velocity? Now we go back to our first year in physics, university physics. I have energy. How do I pull out of it velocity?
On the kinetic term.
Waves.
Waves. The derivative of omega by k, right?
Of E by K.
On the dispersion
Or
equation.
on the dispersion
Oh,
relation.
you meant wave
Yeah.
velocity, not
Wave
velocity.
Omega
velocity.
divided by k, the derivative, whatever. That depends what you want.
The only thing I have to take care for is that
Units. Epsilon is energy, right?
epsilon is energy, so what am I missing here?
H bar.
H bar. Right. 1 over H bar. So,
You can write that also as the derivative of epsilon by the momentum, right?
right? This is exactly the momentum
Yeah.
H bar K. Okay, so I can go and calculate if phi is equal phi 0, so, sorry, if phi is equal 0, whatever the velocity here is, the opposite velocity is a minus sign, no current in general, because I sum up all the occupations here, all the electrons that are occupying this ring, and I get 0 velocity. If you want to be really philosophically, what happens if your filling is even? And the last state will be, on average, half filled in each direction against 0 velocity. What happens when I have a flux? So each point n is shifted by some amount down so I get some current for each state that is not exactly cancelled by the opposite current, because this guy is a bit below, this guy is a bit above. So you have your current. Now, this current is persistent current, right? As long as electrons occupy this ring, they'll continue forever. So two amazing things about this statement. One, we have a flux that is not connected to a magnetic field, and nevertheless creates current in the ring where no magnetic field exists. In a sense, this is a topological effect. What do I mean by topology? The fact that in the center of the ring you have something, if you know anything about topology, that's the mathematical treatment of geometries that have holes in them. A ring is a very good description of geometries that has a hole in it. The mere fixed fact that you have here a different topology where the flux goes through creates current. That was perhaps the greatest achievement of Aharonov Bohm. It, for some reason, started as Bohm Aharonov. Since Bohm died 30 years ago, it made the switch into Aharonov Bohm effect. And basically, you have an effect of flux, although you don't have a field there, which is amazing. And you can't even give the usual explanation in quantum mechanics. The wave function touches the field somewhere. It doesn't touch it anywhere. It lives on the ring and you have no magnetic field on the ring. Okay? The second thing is, according to this result, you can... What is the most basic property of associated with conductance? Anyone who touched any electrical appliance ever felt that it is hot. So, if I have current going, our intuitive expectation is that we'll have dissipation, we'll lose energy. If we have here dissipation and we lose energy, this current should stop. So if we're thinking about the usual case where phi depends on t, okay, we have a changing field, energy is not conserved, it pumps energy into the system. And okay, here we have our heating. Here we have a fixed phi, and we get as our steady state solutions things that are carrying current. Is something wrong here? Well, we may feel a bit bad about it, but the answer, no, it's a persistent current that continues forever.
But you cannot extract it, right?
You can't extract it. You can't use it as a battery. In a sense, it's the brother of the effect of having an electron in the L equal 1 state and asking how does it turn around? How has it angular momentum? Why isn't it lost? Why isn't it dissipated? It can't be lost because you don't have a lower energy that you can go down to. And considering this problem, we opened a new can of worms. Why? Okay, so we started about expressing conductance in quantum mechanics by the question we have to have, if we want to consider a finite system, conductance is an extended system behavior. How do we think about it? How do we approach it? Okay, so we found here some way to do it. But now we're hit by another problem. When we are talking in classical physics, especially in electric conductance, we are talking about a property that has dissipation. When we're writing down a Hamiltonian, steady state Hamiltonian, what is our first conclusion from writing down the Hamiltonian?
There's no dissipation.
Energy is conserved, otherwise what are we doing here at all? So energy is conserved, so you can't have dissipation. So in any calculation where we have a pure quantum mechanical calculation, we're not describing a dissipation, we're describing the dissipation as a process, no dissipation. So how do we connect those two things? Almost last lecture. And as usual, when we're running into a deep conceptual problem, we find at the end of it Einstein. You remember that we expressed something as a perturbation, as a fluctuation dissipation connection. So from some behavior which doesn't lose energy, we can conclude things about processes that lose energy. There you run into, using this kind of behaviors to describe a solid state system, we have to always be very careful. That's why I call the course 50 ways of you're running into problems that you have to circumvent very carefully not to get stupid answers. But if you can do it, I'm not going to go into it in this lecture, but you see why conductance wasn't the mainstream of our this course, because it's delicate and needs a lot of thought. Okay, I said something about a project. Small home assignment. Okay. We calculated V of n. Okay. Excuse the minus, as I repeated endlessly here, I didn't define the sign of the electron. Let's say I have n electrons filling up a ring. Now you can do one of two things.
Units? It's unit per length or something. Current is coulomb per second, it's coulomb times meter.
Right, I have to
current density or something.
excuse me?
If you divide by the volume, then it's the current density or something.
And basically, just a moment, I want to deal. No, I don't think you on the field state. Okay.
The field state, maybe it's units of 1 over m. So
Wait.
over meter.
There should be some meter or something like that.
What is the problem?
Units of current is
Current is velocity times E times
n, which is
density. Okay, so you'll have here divided by L.
okay.
Density. Okay. Yes, I can. Could do it also through this is I. Just check, see that it gives you the same result. Okay. Let's write down this problem as a tight binding problem. What did I write down here? To take binding description of the Hamiltonian, which we have seen a couple of lectures ago. The fact that I'm dealing here with a ring implies that I have to be a bit careful about the last and the first site here. So if I'm writing I equal 1 till n, I have to remember that n plus 1 changes to 1.
It's modulo.
Right. Okay, that's lovely, but that's the case where phi is equal 0. Now a few things that I would like you to convince yourselves. Okay, let's assume E equals 0 just to make life easier. Okay? So I don't put the bottom of the band at some value, I put it at minus 2t. Okay? Let me switch to J just. Why is this minus here? Or permission conjugate, otherwise my Hamiltonian is not Hermitian. And I can't allow that to happen. I take a complex conjugate of this guy, I get exactly this guy, Hermitian conjugate. Okay. So how do I do a calculation with this? I write down a matrix. Okay, I have 0 on the diagonal because I decided so.
You just choose the base that the first term will vanish.
I have no. Oh, this constant. And very important, on the two edges, I have E minus t minus e phi over phi 0. Because here, if I'm going here from 1 to n, right? 1 to n is the other way around, so it's minus, it's not plus. Going back. Still, it's still a complex conjugate. Everything is okay.
You have t squared, so you have t in the sum and outside the sign.
No, the t
one of them,
in the
or
left.
J.
do you want one t?
No, I have.
In the left.
Ah, here I just add.
But also,
Yeah, I just wrote it inside and outside. Okay. So, how do you calculate the persistent current? Take this guy, get its eigenvalues, calculate it for different values of phi, perform derivative, meaning just subtract the value of some jump you are doing in phi minus the value at phi, the previous phi. And you can plot here as function of phi what is the I according to this definition. Okay, so what are the stages? First, write down a metric. First, decide what's the size of the system you want to consider. On a modern laptop, diagonalizing a 100 by 100 matrix will take less than a second. So size is not such a problem. You want perhaps to calculate it for 100 values of phi. No problem, it's 100 seconds. So sit for 2 minutes and wait for the computer to finish it. Calculate the derivative. Decide, let's say you are doing something with 100 electrons, decide to fill up, let's say 20, 40, 50, whatever you feel like. Plot I, that's the assignment. I as function of phi for 5 for an additional grade of 5%. This is open only to people that are here. In order to verify that you're here, if you're intending to do this assignment, send me an email now. Okay, so if someone is there. Now, a fun fact. I could forget about all this elaborate structure. Sorry, I have choose t equal 1, whatever you feel like. Okay. I could rewrite this matrix by eliminating phi on all the diagonals and replacing it here and here by n times the flux. Why is it physically correct? Because the important physical thing is an integration over the loop is equal to the flux. Doesn't matter where on the loop I put it.
The size of the matrix, what defines the size of the matrix?
The number of sides. So that's what I said, choose.
Like the sites, energy sites, or sites like physically?
Well, if you want a simple answer, it's the discretization of the ring to how many points you break it up. In reality, and now the last thing about reality. Okay, I gave you some theoretical concepts. In 1990, someone actually took 10 to the 6, 10 to the 5 rings, put it on a silicon wafer, 10 to the 5th metallic rings, put in a constant flux, and measured for weeks the current in the rings. Was a persistent current. Why 10 to the 5 rings? Because the total current is small. How does he measure it? He can't connect an ampermeter to it.
The induction?
If I have current going around, I have a diamagnetic response. I have a change in the magnetic field going through the system. That was measured. I needed 10 to the, well, not I, he needed 10 to the 5 rings in order to get a big enough response. 92 and 93, they already measured it for 1 ring. They got much more precise. And the persistent current exists, measured, and fun fact. Now, if you think about it, and similar to our model, let's say I would ask you what is the persistent current going through a benzene molecule. A benzene molecule is 6 carbons in a ring. You have the same behavior. That was measured only 20 years after that, for the simple reason that the flux going through a very small benzene molecule is very small, so you have to either put it in a very strong magnetic field that creates different types of problems, or you need a very exact measurement. That was achieved a few decades after it. Okay, just last remark about this behavior. Someone knows what it's called mathematically? Replacing the local phase by a global phase.
Gauge invariance.
That's gauge invariance. You have here the concept of gauge invariance. To those of you who have heard the term, a very simple case of gauge invariance. You can try it on your when you're writing the code. Check it out. Works. Questions? Okay, so I'll see you next time there in the on tomorrow, where I'll basically do a quick run-up on the material, and if you have specific questions, please ask.
התחלתי לעשות חזרה על החומר של הקורס, של ההרצאות, והבנתי, אחד מהמאמרים